Hi everyone, and we're going to talk about the chapter 5 today. And then also you need to finish two assignments. One is the quiz you have. Actually, I will already post an assignment. The other is in class practice or exercise. So today's content will be chapter 5.1 and chapter 5.2, and we will do about the confidence interval and the sampling distribution of sample portion. Okay, so last time we talked about a population, and then if we understand about the central tendency, which is the average, and then we can build up this kind of distribution, and then we call this is x-score. And then if this is a follow the normal distribution, so this curve is go by normal, and then we can do standard normal distribution. So this is a standard normal distribution. We can transform our data from mu to 0. That means the central point is 0. And then sigma equals to 1. So, and we can base on this distribution curve and find out the probability. Of course, these two probability is the same. So what we're going to do is like that. We can figure out exactly the score and then use 185 minus mu and then divided by the sigma. So we can find out the z score in this range. That means how many sigma in this range. So you know the difference of population distribution as well as sampling distribution. So population distribution, sometimes we are very difficult to find it. And then we will use the sampling distribution. For instance, if you want to understand what is the people feeling of the United States, and then if you want to do that, the population will be the whole population of the United States. So we cannot do the census of the data. The only way we can do it is that we're going to do the sampling. It's easy sometimes, and in this class actually we don't talk about the sampling method, but we're going to teach you the most simple way to do the sampling distribution. So for instance, in engineering, we test the strength of a metal rod, and then we know that the population was 33, and then we find out the average is 49.4, and the standard deviation is 2.2. So we can make a histogram here. So we call this as a population distribution. When we do sample, that means I cannot get the 33 data, and then I'm going to do sampling 5 data sets. Okay, so in this kind of sampling, and how many ways you can choose 5 values? Think about it. It's a combination, right? So it will be equal to 33 C5. So you are going to have 237, 300,000, and 336 different kind of combination. So if we got that, and then do all of the means by using computer to calculate, we call it, this is a X-bar distribution. So that's all of the samples we did that. Did you remember we do the first lab? We select 100 data and they randomly select 30 and make an X-bar. So now you see that now the number is about 233,336 different means, right? So, and how about the means distribution? So this is a means distribution. And if you look at this distribution, is it normal? It's just now this distribution is not population distribution. This distribution is the average distribution. That means all of the means distribution. And this is a different than population distributions we have. This is 33 data sets we have. And then you see it looks like not very normal for this case. This is X. So now you know the difference of X and X bar. So we know the mean is 49.4. Okay, and this means is equal to the mean of population distribution. Okay, is equal to mu. Okay, and then standard deviation, which is different than 2.2, it will be 0.911 and is equal to the sigma divided by square root of 5, because the sampling size we have now is 5, and we are calculating the distribution of the means. So sampling distribution is the distribution of sample means over repeatedly samplings from a population. And you see that this is actually we use X bar, follow the normal distribution approximately with a mu equal to 49.4, and then the variance, because now it's a means distribution, so the variance will be equal to the variance of distribution divided by sampling size. So in order for the distribution of the sample means to be normal, the distribution of population for each of the sample was drawn should be normal. But is it real true? Always true? So this is the lesson class we talk about the central limit theory. So you see that we can get a set of data, and then we look at all the X bar, and then we look at the X bar distribution, and it will be normal. And this is actually can be calculated, verified by calculus. Okay, and then this is why the results we have, which is follow these equations. Okay, and then we can go back to the original one. If they are normal distribution, and how about the central tendency range that based on your sampling? Because now we are looking at the central tendency of the data. So we look at your X bars distribution, and we want to understand what is the probability of 95% the distribution of mean. So record the class we have in the last week, and you know that we can make a tail test of the area. So now you know that 95% of the data, Z will equal to 1.96. This area is 1.96. And this is a 2 regions test, and then the alpha is equal to 2.5%. That means we have about 2.5% uncertainty of our data. And then we can look at the X bars distribution, the critical numbers will be equal to mu plus your z-score and then times the standard deviation of the errors. And then we can estimate the data of the mean for the confidence level of 95, which is will allocate between 47.6 to 51.2. So, and then we can estimate the population means now, okay? And then we random sampling of 5, and this is we call it a point estimate, okay? Point estimate. And then we know that this is a point estimate. So let's go back to see it again. Why is a point? Because we randomly select one set of the average. We call it X bar, and that is belonging to the case, actually 1 of 236,336 samples means. So this is a 1 of the point estimate. So let's look at the next step. So we know that, and then we know the standard deviation of the error will be equal to 0.911. So this is saying that 95 chance that your point estimate is joined with the red area. So now we're going to talk about confidence levels. So that means we're going to use the theory to estimate of the population means. Okay, we are not asked estimate a population range, but we estimate of a population means. Okay, and in statistic inferences, we wish to estimate population mean using observed sampling data. So we always check our central tendency, and this will be the most important things we want to understand. So a common problem in statistics is to obtain information about the mean of a population, and this is a questions, right? For instance, we understand what is the mean gas mileage of a new model car, or what is the mean starting salary of CBU undergraduates. So we do the point estimate. With sampling, we find out the average. But you know this average has some error with the real population means. And we know that X bar is not equal to 0, mu, right? Last term we have, this is about 50, and this is 49. So, and then better way to estimate a population mean with your sampling mean. How to do that? And then we can estimate a certain range of your data, and then say what is the range of your data compared with exactly the population means by a range, and we call this is a confidence levels. And then point estimate, we know that is not exactly the data, but we can say that the data is in a range. We call it interval estimate. And it's similar like we say how cold of the day and what is the temperature of the day, and you give me a range. So now you give me the range is central tendency range, but it's not the population range, right? Okay, so let's look at the examples of interval estimate of a population mean. So the starting salary of undergraduates in the United States, we know that's a mu. And then we know the standard deviation is known as to be $3,200. So we random sampling 36, seem like our class graduates, and then we find out a point estimate, which is $49,280. So we know that a simple sampling, sample size is 36, and then we know that we can make an estimate by standard deviation of the arrows, and which is equals to 1200. And then we can use this to estimate interval estimate of a population means. And what is the number of that? Now you know how to calculate, right? So it will be equal to 1.96 sigma. The sigma x bar, right, in this range. And the central tendency point minus 1.69 sigma, lower. So this totally is 95%. Right? Or if we want to look at, again, if we want just look at alpha, we can use this formula to calculate. So, and you will know that. So let's say the data range, we call it interval estimate, is about 1.96 standard deviation of errors above and 1.96 standard deviation below. So this is the range of the data, which is the we find it out, right? So, and then you find out the interval estimate is equal to $4,704. This is within 95% confidence interval. So this is a drawing of that, and then now we can see that we find out that, and then we say 95 of the data, which is a chance lie in one average like that, and within a range which is about 1.96 standard deviation of error, and below 1.96 standard deviation of errors, and that is the data distribute. Right? So in the other words, and we can say that the 95% confidence intervals, the intervals from x bar plus minus 1.96 standard deviation of errors around the single sample means has a property that is the population means is captured. Okay, so that is what we say that the data we have, which is 95%. Okay, so now you know that the importance of that is confidence intervals for the means. So we know that we can express that as this kind of formula. So you see, now you know that x bar distribution is the mean, and that is allocated between negative 1.96 standard deviation of errors or and between and plus 1.96 standard deviation of errors. And since we don't know about this, and we can rearrange the expression by x bar. Okay, and then this tells us that 95% of the time the true means should be lie or should lie within plus minus 1.996 standard deviation of the errors of the sample mean. So we can show like this, and this is exactly what the experiment we have from the 36 data. And then exactly population means maybe go like this, and maybe go like this, maybe go like this, and maybe go like this, and maybe go like this, right? So this is the population means distribute in this area. And then we can think about that, the different sampling. Okay, for instance, the first one, we did that. We do the second times test of the data. We do the third times test of data. We do the first times, 5 times, 6 times, and so on and so forth. So you can do a lot of tests, and then your conclusion will differ. So it depends on your samples, right? The first time, second time, and so on and so forth. So we were going to dealing with the problem of confidence level. And alpha means uncertainty. We talked about that before. Or we call it errors. And versus probability of capture the true means. The first question is asking, does the confidence interval equally or does the confidence interval actually cover the population means, which is mu? And there's no way to know for sure. But if you repeat the sampling, and then 95% of sampling intervals will be covered the actual mu. Okay, so the confidence levels gives the probability that the interval will capture the true parameter value in repeatedly samples. So now we look at some examples. Okay, one example. A sampling interval gives an estimated range of the values which lies to include an unknown population mean. Okay, and this is an example. In a sample of 123 hip surgery of a certain type, the average surgery time, so this is time, was 136.9 minutes with a standard deviation of 22.5 minutes. So we know that sampling size we have now is 123. So we know the average point estimate, which is 136.9. And we also know the standard deviation is equal to 22.5 by these samples. So what is the confidence intervals for the population mean at the 95% confidence level? So we want to understand the confidence intervals, right? So now we know that you can calculate that, and based on the data we have, so we know the confidence level of X bar distribution is within these two values. Okay, and then and this is actually the calculation of the z-score times standard deviation of the errors, right? So population, it looks like this, and then the other one is like that. Suppose we take a sample of 75 students from CPU and record their family incomes. Suppose the incomes in thousands of dollars are this data set. And we know the X bar is 89.96 and standard deviation is 51.68. Find a 95% confidence interval for the population mean of family income. So we can do now by the equations, right? So we do the calculation and then follow that, and then we can find out the boundary, right? And then we can find out the confidence level if the sigma is null. Okay, sigma is null. So we know the standard deviation. Okay, so a confidence level also can be changed to 90, right? So if you change to 90, we did this before, and this score will be equal to 0.05 here, the other 0.05 is here. So totally added is 0.1. Alpha is equal to 0.1. Okay, so it's divided by 2. We call it 2 tails. Okay, and then we try to find out the range. And you go to the table, and you will find out Z score is equal to 1.645 sigma X bar. So that means the data from here to here is 1.645 sigma X bar. So, and of course we can change the alpha. Okay, you change the alpha, and you will find out actually the Z score has been changed, and because they can allow more range of the data spread in the area. So this is 1, 2, and 3. So you see that this is for 99%, and that will be Z score will be 2.576. Okay. So if we want to estimate a population mean of your sample mean, so we need to know those parameters. The first one is standard deviation. Second one is average of the population. The third one is the sampling size. The last one is the level of confidence for your estimate. So let's look at the equations again. 95% is like that, right? And then this is the equation shows that why it is like that, right? In the 2 range, because divided by 2, this is 2 tail, right? And then you can see this by the equations. So this is divided by 2 because both of them are equal, and this shape is symmetric. So 95% confidence intervals, it will be equal to X bar plus minus 1.96 times standard deviation of errors. And then also you can change when the confidence intervals is different. So the more precise or lower confidence levels, okay, this is a lower confidence levels, and then this is less precise, and this is a higher confidence levels. The other question is that, can we get more precise while keep a higher confidence of our estimations? right? And if you look at here, that the equation is confidence level is changing by these factors. The one of the first factors is based on the errors of alpha or uncertainty of alpha. The second one is based on your standard deviation divided by your sampling size. So when we increase the sampling size, and we can reduce the range because these become larger, and then the whole items become smaller, and then this range can be smaller. Okay, let's look at one examples we have. Sampling mean and the standard deviation for the field weights of 100 bucks are: make a sample which is 12.05 and the standard deviation is 0.1. And how many bucks must be sampled to obtain 99% confidence interval with the width plus minus 0.012 ounce. Okay, so the units now is ounce. Okay, so you can do the exercise, right? And show the answers. Okay, let's move on. Next one, and which is the sampling distribution of sampling proportion. And then I think we should break here, and it's already about 40 minutes, and I hope that the rest of time you can figure out how to solve your quiz free and upload on the Blackboard. And I think this is the end of today's class.